Hi class, today I'm going to go over this worksheet, not the whole thing, but if you're having trouble with understanding what to do and how to figure out the information, I will go over an example or so on each of the sections to help with any confusion that you may be having. First of all, at the top, the first section is on atomic structure. So if you look at the periodic table, be sure that you can label what all the numbers and symbols and whatnot in the boxes represent. So please label the four arrows and what they mean. Check out your periodic table or your notes to do that. The second part is with the big table down here. A lot of students forget to do the top boxes. Don't forget to do those. Actually, you should do them first so you know what you're looking for as you answer for each of the elements below. So for example, the atomic number. You should think to yourself, what is the atomic number? And if you need to, refer back to your periodic table or your notes, and you should think, oh, hey, that's the top number that I see on the periodic table, but what that really represents is how many, or the number of protons that the element has. And so that's what you need to do for each one of these boxes. Write down defining information that will help you understand what it is or how you find it. When you get down to the examples, I give you only a little bit of information about each one, and you have to figure out the rest. So for the first one, I give you the atomic symbol, which is Fe. And if you don't know what that is, that's why you have to go to the periodic table. So looking at the periodic table, you have to find Fe, and if I zoom in a little bit, here it is, Fe, which is iron. The top number is 26, and the bottom number is 56. And if you need to refer to that, there's a sample labeled one right here, and you could actually fill that in for the one that I put on yours with sodium. So knowing that the top number is 26, the atomic number, and the bottom number is 56. So coming back here, we're going to fill in the information. The element name is iron. Its symbol is Fe. Its atomic number is 26. Its mass, which is its bottom number, is 56. Now I have to figure out specifically how many protons, the average number of neutrons it has, and the number of electrons for a neutral atom, which are the ones that you find on the periodic table. So knowing that the number of protons is the atomic number, these two things are the same. So you're going to put down 26. The average number of neutrons. So the bottom number, which is the mass number, it is the number of protons plus the number of neutrons, because those are the two subatomic particles that have a significant mass. Electrons, they do have a mass, but we ignore them and do not include them in the average mass. So it's these two numbers together, and guess what? I already know that the number of protons is 26. So this is just a subtraction. 56 minus 26, and that leaves 30 neutrons. And finally, the number of electrons. So in a neutral atom, that's important. Everything on the periodic table is neutral, and what that means, it always has the same number of positive particles and negative for every element. So if I have 26 positive protons, I must have 26 negative electrons, because neutral means that they cancel each other out. Now sometimes I don't give you the symbol, I give you different information. So in this case, the atomic number of the second one is 15. So that means that you need to know that the top number is the atomic number, and you have to find number 15 on the periodic table. And so that's right here, it's phosphorus, number 15, and its mass is 31. So we come back here and we put in that information, and its symbol is P. We know its atomic number is 15, and if you forgot, again, 31, it's the bottom number, is the mass, so we're going to put 31. The number of protons is the same as the atomic number. It represents the atomic number, so you're going to put down 15. The mass is 31, and the mass is made up of protons plus neutrons. I know that there's 15 p's. How many n's do I have? 31 minus 15 is 16. and you need to have equal amounts of positives and negatives in a neutral atom. So if there's 15 positive protons, there must be 15 negative electrons. So I hope that makes sense, and you could finish doing the rest. On the bottom half of the page, we need to draw the atomic structure, the isotopic symbol, and the dot diagram for these four. So the atomic structure is just the simple Bohr's model, which I know you don't know that name, but it's a simple model that we use. So the way that I would draw it is I draw the nucleus, which is comprised of two things. You need to know that the nucleus of an atom, it consists of protons and neutrons, the two things that have the mass. And so it's sodium. So I'm going to go to sodium and find sodium on the periodic table. Here it is. So these numbers become important because I need to know how many protons, neutrons, and electrons I need to draw. So this is the number of protons, the top number, and then 23 minus 11, which is 12, that's going to be my neutrons, and because this is neutral, I know that protons and electrons equal the same thing, so I also have 11 electrons. With that information, now I could draw some stuff. So I know that I have 11 protons. Let me zoom in a little bit. 11 protons. And I figured out that 23 minus 11 is 12 neutrons. Neutrons don't have a charge. And those two make the mass of the atom, and they also comprise the nucleus. And then what I like to do, I guess you can make them solid, but for some reason I prefer, personally, to use dotted lines because the shells or the orbits, they really don't exist in like planetary aspects, and I mentioned that in the video. Electrons can move around wherever they want, but they just happen to be found in certain shells or energy levels most of the time. All right, so if I have 11 protons, I have 11 electrons. There's only allowed to be 2 electrons in the first shell. So you could use dots, you could use E's, you could use whatever you want. Those are the two most common. I'm going to use E negative to remind you they're electrons and they're negative. And I like to kind of space them out oppositely. So there's 2 electrons there. I can't fit more than 2, but it has 11. So I need a place for more to go. Well, let's make a new orbit. So the second orbit. Now here comes the rule of the octet rule. Every orbit after the first one could only hold a maximum of 8 for the ones that we're going to use in biology. So that's the octet rule. So that means that I could put 8 here. So 1, 2, and then I have 3, 4. I like to pair them up. And kind of put 2 on each side. All right, so now I have 10. 2 and then 8, that's 10, but there's 11. Now what? Well, ran out of room. Make a new orbit. So I'm going to draw a new orbit. And I only have 1 left. Pick a spot. There we go. There's the 11th electron. And so this is how I would draw the atom of sodium. But we also have to put the isotopic symbol and the Lewis dot structure. The isotopic symbol is pretty simple. You're going to put down the symbol for sodium. And if you don't remember the symbol, it's not S. That's sulfur. Sodium is Na. These are Latinized names. So you're going to put down Na. And the isotopic symbol puts the mass as a superscript in front and the atomic number as a subscript below. So, if you don't remember, the mass of sodium was 23, so you put 23 there, and the atomic number, which was the top number, was 11. And that's how we would write the isotopic symbol for sodium. The Lewis dot structure represents how many valence electrons. So to do this, you put the symbol, Na is sodium, and then you have to know how many valence electrons it has, and you could just look at the picture you drew. Valence electrons are the ones in the outermost shell only. So here's my outermost shell. I only have one electron there. That means there's one valence electron, and I'm going to represent that by putting one dot next to it. So that is the Lewis dot structure for sodium. All right, so you can do the other three examples now. On the back, so the top part over here is with some isotopes, so answer the questions on the top, use your notes for help, and we're going to do one of these examples for isotopes. So let's zoom in on, I guess, the first example right here. All right, so we need to do the isotopic symbol of nitrogen first. So nitrogen, you have to find it. If you don't know already, it is number 7. Its symbol is N. Atomic number, mass, 7 and 14. So coming back here, isotopic symbol is symbol with the mass as a superscript and the atomic number as a subscript. So do it for the normal one when you do carbon and sulfur and iron as well, the normal one that you would see on the periodic table. Then this is another way to write isotopes. So sometimes we could write isotopes, let me show you over here, we could write isotopes like this, like we call this nitrogen 14, and sometimes we could write it like this is nitrogen 15, and that's why isotopic symbols are useful, but sometimes they're written like this too, it just really depends. So I wrote them this way for these examples, and you have to figure out the number of protons, neutrons, and electrons in those atoms or isotopes. So this is an isotope, and that's the normal atom, and the number of protons, nitrogen is nitrogen because it always has 7. So the top number can never change, because then it would not be nitrogen if it went to 8 or 6. So if it's nitrogen, it has to be 7. That's its atomic number. That's its defining number. The number of neutrons, remember, is the mass, the total mass, minus the protons. So this number is the mass, just like this number is the mass. So knowing that the mass of this nitrogen is 15, 15 minus 7, there would be 8 neutrons. Electrons, this is a neutral atom, so that means if I have 7 positive protons, I better have 7 negative electrons. So it is neutral with no charge. 14 minus 7, nitrogen 14 has 7 and 7 protons and 7 electrons. So you have to remember that these are the masses. On this one down here with iron, I give you the number of neutrons, so you should be able to figure out the mass of iron from the information that's given. So the last part of the worksheet deals with ions. You're given certain information and you have to fill in the rest of the chart. So the element name is missing here, but I did give you the symbol, which is K. Come over to your periodic table. K is right below sodium, Na. It's K right here, which stands for potassium. Its top number is 19, so that's its atomic number, and its bottom number, its mass, is 39. So that's information that's going to be important to us here. So let's go back and put in potassium, and I need to put down the number of electrons that potassium has. Well, if you remember from the previous parts that the number of electrons equals the number of protons in a neutral atom, and the top number is the number of protons, so I have 19 positives, so I have to have 19 negative electrons, and that's how many potassium has. Now I have to figure out the number of valence electrons. The valence electrons are the outermost, the ones in the last shell. So some of you are thinking, well, so I have to draw all these out like I did on the front side with the shells and the nucleus and putting all the electrons in? No, you don't. If you remember from the notes video, I showed you a trick with the periodic table on how to figure out that information very quickly. So the periodic table, which you'll learn in chemistry next year, is set up in a very specific way that tells you a whole lot of information. So the first thing is that the columns in the periodic table are also called groups or families. And you can number them, we are going to number them, and the number that column is the number of valence electrons. So everything in this column 1 is going to have 1 valence electron. Everything in column 2 or group 2, 2 valence electrons. Now it drops off here and dips down. These are transition metals. Transition metals go by different rules. You'll learn it all in chemistry, but here in biology, we only care about these 8 columns. So column 3, 4, 5, 6, 7, and 8. And like I said, the most electrons you could have in a shell is 8, the octet rule. In chemistry, transition metals go by different rules and can have more than 8, but you'll learn that next year. In biology, we go by the octet rule, the most being 8. So, group 1, potassium's in group 1, it has 1 valence electron. So that means we could come back here and put down that it has 1 valence electron. Now we have to do the dot structure, and just like we did on the previous problems, that's how many valence electrons it has in dots. So 1, there you go. And then we need to know the number of electrons it needs to gain or lose to become stable. Remember that the word stable in chemistry means a full valence shell. And it does not have a full valence shell. A full valence shell is either 2, if you're really tiny, or it's typically 8. And potassium does not have 8, it has 1. And so it's going to try really hard to make sure that it's full somehow. And there's 2 ways that you could become full. You could either lose what you have, lose the electrons that you have, and drop down to your full shell below, or you could gain more and fill up the shell that you currently have. So your valence shell, it could either get rid of your electrons and drop down to the next valence shell, which is full, or you fill up your current valence shell. If we're at 1 for potassium, potassium could do one of 2 things. It could lose 1 and drop down, or it could gain 7 more and fill it up. Which one do you think is easier? It's always the lesser one. So in this case, it's much easier for potassium to get rid of 1 and lose 1 than it is for it to find 7 more. So I'm going to write down it loses 1 electron. The chemistry and physics behind that, you'll learn in chemistry next year, dealing with electronegativity and such, but that's an easy way to figure it out. Now, knowing that it's going to lose 1 and get rid of this electron, I need to know its charge. So you have to write down its charge. So if you lose 1 negative electron, you're going to lose a negative. And if you lose a negative, you become positive. So you're going to write the symbol, which is K for potassium. Now when you normally write K for potassium, it means neutral. So potassium would have 19 electrons and 19 protons, right? And 19 positives, 19 negatives, neutral, no charge. And that's why we write K, like we do over there. But now what's happened is that we actually will always have 19 protons, because that makes potassium potassium, but I just lost 1. So if you lose 1, you're down to 18 electrons, and I have 19 positives and 18 negatives. So overall, I have 1 more positive proton. So this gets a +1 charge. Now, you don't have to put the 1, it's assumed, but I like to put it just to make sure you know what you're doing. The next one is S. S is sulfur, and actually it's right here. Sulfur is number 16, the atomic number, and its mass is 32. So let's do this one real quick, sulfur. And the number of electrons sulfur normally has is 16, because that's how many protons it normally has, and so it has to have the same number of electrons. And let's see what column it's in. Well, it's in column 6, so it has 6 valence electrons. So now that we have to do the dot structure, we have to put 6 dots, and you could start and kind of go around 1, 2, 3, 4, 5, 6. I'm not going to be picky about where they go as long as there's 6. Don't put more than 2 dots per side on the left, right, top, bottom. All right, so here's the choice you have to make. Sulfur has 6 valence electrons. It needs 8, right? So it could gain 2 to get 8, or it could lose 6 and drop down to its next fullest shell. Which one do you think is easier, to gain 2 or to lose 6? It's always the lesser one, it will gain 2. So we're going to write down gain 2 electrons. And now, normally it has 16 protons and 16 electrons, but now it gained 2, and now it has 18 electrons. So that means I have 2 more negatives. So overall, I have more negatives than positives. And again, if you need to write it out, do it. So 16P, 16E, that's normal sulfur. But if we gain 2 and we go up to 18, now we have 2 more negatives. That's going to give it an overall -2 charge. So you're going to write the symbol -2, and that's the ion it became in order to become stable. And that's what you're going to do for the rest of them. Hydrogen might be a little tricky in a certain sense, so just pay attention to that one, but the rest should be okay. Pay attention to the last 2 as well and the column that they're in, and think about what would happen to neon and helium, them being actually right here in the last column. And finish your questions at the bottom too. And I hope that was helpful, and I'll see you in class. Bye.